Hello, Allegheny College Introductory Astronomy students, and welcome to another session about astronomy. Today we are going to be going over the end of chapter 14, talking exclusively about black holes. Today's class will end a section where we've been talking about stars, and looking forward after that we'll next talk about galaxies, and then we'll finish off the course by talking about cosmology and the search for life in the universe. Today's astronomy picture of the day, I chose one from last year, back in April. That was when you had the first detected, or the first imaged, rather, black hole. And this particular galaxy that we're looking at is M87. We'll talk about it today in our class. And this background image is zoomed out. And you can look in and you can see something exciting is happening down here in the center. There's jets of material that are flowing out. There's gas which is orbiting around. As we'll discover, there is a black hole there that is billions of times the mass of the sun. And then here is that image that was first taken less than a year ago of a black hole and of the matter that's surrounding it. So we'll spend a little bit of time today talking about this particular case, in fact. All right, last time, remember, we were discussing how mass warps space. And we said it also warps time around the mass as well. Really, any form of energy will do that. And what we mean by that it warps time, we'll explore more today. As you go to different places in a gravitational potential well, time will run at different rates. Your clocks that you have on your wrist, they do not run at the same rate. It depends on how fast you're moving, and in this context, it depends on where you're located and how close you are to a gravitational source. We also saw last time that as an object collapses down while maintaining the same mass, the escape velocity from its surface is going to be getting larger and larger and larger because it's got a larger distance to go to make it all the way out to infinity, but the same mass is pulling it inward. And so that additional extra distance it's got to travel after the object has collapsed a little bit means that it has to have more energy, more speed to be able to ultimately make it to infinity. So this allows us to define a quantity that we mentioned last time in passing, now a little bit more carefully. What I'm thinking about here is the surface, or the so-called event horizon of a black hole. The event horizon is a good name. In physics and astronomy, an event is anything that has a position in space and a moment in time. So if you snap your fingers, you could give an x, y, and z coordinate for that event. You could also give the time at which that happened, and those four numbers then specify a event. So everything that happens in our universe we could consider an event. And an event horizon is something that is a boundary past which you cannot see the events that happen. You know what a horizon is, right? Your significant other gets in a pickup truck and drives off into the distance. And as they pass over the horizon, waving to you, you no longer can see them because they're on the other side of the horizon. Well, likewise, in black holes, if you are inside the event horizon of the black hole, then that event that occurs there cannot be seen by someone outside. Because what the event horizon is the surface inside of which nothing, not even light, can escape. And so imagine an event occurs inside the event horizon. The light, imagine you tried to shine it outwards. It can't go outwards. It gets pulled inward toward the singularity. And so if the light cannot get out, that means nobody outside the black hole can see what happened. That event is past the horizon. The radius of this event horizon, at least for a non-spinning, non-charged black hole, it's called the Schwarzschild Radius. And so the Schwarzschild Radius is the radius of that spherical event horizon. So we talked a little bit about this last time too, and now we can extend this to the context of black holes. If you had no mass in your system, then space-time is flat and objects would just move along on straight lines. You can think about space-time as being represented by a rubber sheet. And if there's no mass to deform that sheet, objects just roll along on straight paths. As you put some masses down, you deform the sheet. And we saw last time how you could explain the orbits of objects around by thinking about the curvature of the space due to that mass. And if you compress and condense the mass enough so that it becomes a black hole, then you open up a throat, so to speak. And in these two images here, let's say the mass of this star and the mass of the black hole were the same. Notice that at a given distance away, the curvature is the same in the two cases. Like the curvature of the sheet there is the same as the curvature of the sheet here, right? And that's because the masses of the star or the black hole were the same. Where it starts to differ is before you could only go into the surface of the star. Now you can get closer and closer and closer to the center because the black hole is not taking up that space. One neat thing about black holes is that they warp space so much around them that you can actually have light go in circular orbits, right? And so at a particular radius around the black hole, the light could just orbit. And what that means is, imagine you were at that radius, let's say you're here. If you were looking off that direction, what would you see? You would see light from the back of your head that orbited all the way around the black hole to enter your eyes. So you have your telescope, light comes off the back of your head, orbits around the black hole, and comes into your telescope, and you could see through your telescope the back of your head. There's some interesting orbital paths that happen around black holes. Okay, this Schwarzschild radius, remember, that defines the size of the event horizon. It has a very simple way that it can be calculated. It turns out to be about 3 kilometers for every solar mass of the object. And so you see right away that if you have a more massive black hole, that's what M represents here, you'll have a larger Schwarzschild radius. And here's a little interactive figure that we can play with. Right now, the black hole is 3 solar masses, and its Schwarzschild radius is 3 times 3, or 9 kilometers. And as I make this number bigger, so now I'm up to 430 solar masses, 4.3 times 10 to the 2. And if I multiply that by 3, I get to 1,290 kilometers. And so the larger that you make this, the more massive that you make this. And vice versa. The more massive you make the black hole, the larger its event horizon. So it's a very simple relationship to calculate Schwarzschild radii from masses of the object. So for example, if you had a 3 solar mass black hole, its size is 9 kilometers across. Not across, but rather in its radius. The diameter would be twice that, so to speak. Remember last time we said that neutron stars had typical sizes of about 10 kilometers in radius. So a 3 solar mass black hole, insofar as its event horizon spreads out, is about as large as a neutron star. Okay, so here's Bella. Bella, there's a slide about you. And imagine that you were to take Bella, who weighs at the surface of the Earth about 15 pounds. And that corresponds to about 7 kilograms of mass. And let's say you wanted to crush her down. No one wants to do that, baby. But let's just pretend you crush her down to make her into a black hole. How much would you have to compress her? Well, we said her mass is 7 kilograms. What we want to do is basically convert that to solar masses. The mass of the sun is 2 times 10 to the 30 kilograms. So if I take the ratio of these two numbers, I'll get her mass in solar masses. That's what I've done here. 7 divided by 2 times 10 to the 30. She's a mere 3.5 times 10 to the minus 30 solar masses. That's her mass. And so I need to multiply that by 3 to get her Schwarzschild radius in kilometers. 3.5 times 10 to the minus 30 times 3 is just a little bit more than 10 to the minus 29 kilometers, which is 10 to the minus 26 meters. Now for comparison, the size of a nucleus of an atom is about 10 to the minus 15 meters. So this is 10 to the 11 or 100 billion times smaller than that. So you would really need to crush down some object like Bella to this very minuscule size. But if you did that, then she would be a black hole, right? Because the mass would have to collapse further down to a singularity. Typical people, let's say, have masses of 150 pounds. Obviously, some are more, some are less. I'm a bit more than 150 pounds, quite a bit more. But the idea is here, people are, say, 10 times more massive than Bella the cat. So our Schwarzschild radii would be not 10 to the minus 26 meters, but about 10 to the minus 25 meters. Still very small. So any object has the potential to become a black hole if somehow you were able to crush it down. How far would you have to crush it? You'd have to crush it to within its Schwarzschild radius. And then gravity would have no choice but to turn that into a black hole. All right, so how does the radius of the event horizon change when you add mass to a black hole? It's a question for you to try to answer. A, it increases. B, it decreases. C, it stays the same. Please pause it if you need to. Pause it if you need to. Okay, so the answer is that it increases. Indeed, a more massive object, more massive black hole, will have stronger gravity field. The location at which the escape velocity becomes the speed of light will be further out, and so the Schwarzschild radius, which is the distance to that location from the black hole, is going to be larger. A is the answer. So if you took the sun and you shrunk it down, you could turn it into a black hole. There's no reason that you could do this because the pressure of it will prevent you. But imagine you're a supernatural being. How much would you have to shrink it down to? Well, 3 kilometers is the sun's Schwarzschild radius because it has 1 solar mass of mass. And you multiply by 3 to get 3, and that's the Schwarzschild radius in kilometers. And if you crush the star, the sun, down to 3 kilometers in size or less, then it becomes a black hole. Now, one thing to note, if you were to do that, is that it's still the same mass as before, still 1 solar mass. So the curvature of space-time around it, as long as you're at locations that are outside the radius of the pre-shrunken sun, is going to be the same. Here, you see it's the same up here as it is down here. The only thing is that if you get close enough to the black hole, then you start to get to these highly warped regions. But if magically the sun turned into a 1 solar mass black hole, the Earth would just continue to go around on an orbit. 8 minutes later, it would get very cold because the sun would no longer be shining. But in terms of the orbital motion of the Earth and all the other planets and everything else in the solar system, they would all just continue exactly the same as before. It doesn't matter that the object in the center is now a 1 solar mass black hole rather than a 1 solar mass sun, because both have the same gravitational influence on things that are outside of the current radius of the sun. So there's this misconception that somehow black holes suck in everything, and if we were to replace the sun with a 1 solar mass black hole, everything in the solar system just gets sucked into the black hole. That's not the case. It's actually pretty hard to hit black holes. You have to be sending the object right at the black hole, or very nearly at the black hole, because if you have a bit of sideways velocity, then that could be enough to have it orbit around the black hole and avoid falling in. So what would it be like to visit a black hole? There are a lot of different things that can happen. Most of them will kill you. And so let's talk about some of them. On this slide, we're talking about gravitational redshift, and correspondingly, we'll flip it in a moment to also talk about gravitational blue shift. You've heard these terms redshift and blue shift before when we were talking about the Doppler effect. Remember, redshift is when light gets spread out, its wavelengths are stretched, whereas blue shift is when the light has its wavelengths compressed. And so here in the context of black holes, or really just any gravitational mass whatsoever, what we can think about is shining light outward. And so imagine that you're outside the event horizon of a black hole and you're shining visible light outward. As that light goes outward, it doesn't slow down. It's not like if you throw a ball outward, the ball starts moving more and more slowly as it gets further and further away. Light always travels at the speed of light. That's the way it is. That's one beautiful thing about nature. You couldn't have predicted it, but you could make that hypothesis and then test it, and you say, doggone it, light always travels at the speed of light. And so it does lose energy, however, as it moves away from the gravitational source. And it does it not by slowing down. It does that by stretching out to longer wavelengths. Remember, longer wavelength light is less energetic light. And so what was originally visible light can become infrared and then radio as it moves further and further out. Or if it initiated as an X-ray beam, then that X-ray could become ultraviolet and then visible and so on. It could get weaker, less energetic as it moved outward, but always traveling at the speed of light. Now, if you reverse it and you imagine shining light in toward a black hole, again, the light's going to continue to travel at the speed of light as it moves closer and closer and closer to the black hole. But the way that it gains energy is by getting blue shifted. That is, the wavelengths become compressed. And so if you were to reverse this and imagine shining inward visible light, and then as it falls towards the black hole, it becomes ultraviolet and ultimately X-ray. And I should emphasize here that although this effect that we're talking about, gravitational red and blue shift, is at its extreme in and around black holes, it's true of any gravitational mass. If here on the surface of the Earth, if I shine light upward, as it moves upward, it is gravitationally redshifted. Or if I shine it downward on Earth, it gets gravitationally blue shifted as it comes down. This is really an effect of gravity, not an effect of just black holes. So if you were to imagine, actually let me step back, if you were to imagine going down into a black hole, one of the things that you'd have to be wary of is what's called the blue sheet, because you're falling down into the black hole and light from the rest of the universe is shining down on you and it's getting blue shifted. And so what was previously safe radiation for you would become unsafe. It would become shorter and shorter wavelength until ultimately it could become X-rays and gamma rays and fry you to a crisp. It would be dangerous. So as you approach event horizons of black holes, that would be one way that you would die. Here's another thing you'd have to be aware of as you fall towards a black hole. Tidal forces. Remember we talked about tidal forces in the context of the moon and the Earth. Also the sun plays a role, but let's stick to just the moon and the Earth because the moon's effect is larger than the sun's. And the water on the Earth bulges out towards the moon on the near side, and on the far side you're pulling out the Earth from underneath that water on the far side, so the water bulges out there as well. And you have two bulges of water on the Earth, and the Earth spins beneath it once around on its axis every 24 hours. So every 12 hours, because there are two bulges, you have a high tide. And so when you talk about tidal forces, it's always something like the following, or where you have a force that changes over position. In the case of the moon and the Earth, the force on the near side of the Earth was stronger than on the middle of the Earth, which was stronger than on the far side of the Earth. Now imagine the tidal forces on you, the intrepid astronaut, falling down in toward a black hole and its event horizon. Now, the astronaut maybe is falling feet first. And so their feet are closer to the event horizon than their hands are. And so imagine what that means in terms of the forces. The force per unit mass on the feet is stronger than the force per unit mass on the hands because the hands are farther away than the feet. So imagine that you were falling in and your bottom part of your body is being pulled more strongly than the top part of your body. the net effect for your body is that it gets stretched out this way. At the same time, imagine that the astronaut had their arms extended outward. So these are supposed to be the astronaut's arms at this point, right? No longer are their arms directly above the person's head. Now, the black hole is down here directly below the astronaut's feet. And so this hand out here has a force which is downward and in towards that black hole. This force here on the hand over here is downward and in towards the black hole. So yes, of course there's the downward component. That's what would accelerate the astronaut downward. But notice that one component of each of these forces is inward. And so at the same time the body is being stretched along the direction towards the black hole, it's being compressed inward as well. And there's an official name for this process. It's known as spaghettification, because as things fall into black holes, they become spaghettified. They get stretched out and compressed in until they're a strand like a spaghetti of atoms. A strand of atoms that just funnel down into the black hole. So if you were to try to travel to a black hole, and when this occurs depends on what the mass of the black hole is, it's actually a gentler fall towards supermassive black holes, and you pass the event horizon, would be burned by the blue sheet before you're ripped apart by tidal forces. But for less massive black holes, you will be ripped apart by tidal forces before you reach the blue sheet. And so you imagine falling down inward, your body is pulled apart until you were to pass out, and then eventually you're, unfortunately, the astronaut's body would be pulled apart by this spaghettification. So I mentioned in passing that time runs at different rates in different gravitational fields. And this slide will allow us to explore that more carefully. Imagine that you have two identical spacecraft that are both at a safe distance from a black hole, and they have synchronized clocks. Right now the clocks both read 0. So I'm going to go ahead and press play here, and you see that they're orbiting around. You see their clocks right now are still synchronized. 17 seconds have passed. And in a moment, one of these rocket ships is going to thrust its thrusters and slow down so that it will start to fall in toward the black hole. And let me pause it here because it's already started to fall in just a little bit. And you can see the clocks are no longer synchronized. 1 minute 20 has passed in one case, 1 minute 18 has passed in the other. Now at this point, if they wanted, there's no law of physics that declares that they have to visit the black hole. They are outside the event horizon. So given good enough technology where they can thrust hard enough, they would be able to escape and go on their merry ways. But if they did that at that point and compared their clocks, they would no longer be synchronized because they had been in different fields of the black hole while they were exploring it. This asynchronization becomes more and more pronounced the farther the rocket ship falls in. So here the rocket ship is at 1:30, the other is at 1:54. Imagine this is you here that is on the further away rocket ship, and you're using a telescope to look at the watch on the wrist of your friend in this rocket ship that's headed towards the black hole. You would see that watch ticking away more slowly, right? And if the person waved to you, the person would wave more slowly. Everything that you would see that person do would go more slowly. Now, if you're that person falling in, you don't notice anything different going on. You have your clock, which is just running normally. You take your heartbeat, maybe it's 65 beats per minute because you're cool as a cucumber. You're not worried about this black hole. You look out at your friend far away, and what do you see? You see your friend's clock running quickly. You're like ticking away. and your friend's waving and saying hi, and the further away you look, in fact, the faster everything is evolving in the universe. And this becomes more and more pronounced the further and further you fall in. So as you approach the event horizon and you look out at the universe, you see the universe whizzing away into the future, even though your clock is running more slowly compared to it. Now, another thing to notice on this interactive figure here is that the rocket ship is turning red. That relates back to something we were talking about a few slides ago, the gravitational redshift. Imagine that light is coming from that rocket ship outward to you in a further away rocket ship. That light is being gravitationally redshifted. It's becoming lower energy because it's fighting to get out of the gravitational potential well. And in addition, lower energy means that it's getting stretched out to longer wavelengths. And so if something originally looked blue, light from it would get stretched out and start to look green and ultimately red and then infrared and so on and so forth. So if we watch this rocket ship fall down in towards the event horizon, what actually happens is that its clock will get slower and slower and slower, and it will come to a stop as it approaches and reaches the event horizon. You'd also see it getting dimmer and dimmer and dimmer because you have that less energetic, gravitationally redshifted light coming out from it. And so from afar, you would see that rocket ship kind of go down and become redder and dimmer and just kind of freeze on the event horizon. Now, I have two daughters. One was born in 1996 and one was born 4 years and a month or two later in 2001. About a month and a half, 4 years, 1 month and a half. And so one of them is in graduate school right now and one of them is in college. And so let's say that we played the following game. We took the older student and we said, you need to go visit this black hole. And she says, yes, Dad, I'll go visit the black hole. And she gets in her rocket ship and she goes and she flies down towards the surface of the black hole. As she looks out at the rest of the universe around her, she sees it start to evolve faster and faster and faster than what's occurring for her. And she sees her sister through her telescope. She sees her sister, getting older and getting married and having children and grandchildren and so on. And then she says, I got to go back. I'm not going to this black hole. So she fires her thrusters and she comes back and she goes to see her sister. And now her sister has lived a long life. She's a grandmother, a great-grandmother. But Linnea, my older daughter, she had only been along on this journey to the black hole for, say, depends on the details of the scenario, but let's say there was a convenient nearby black hole for a year. And so she's only a year older. She's in her 20s, where her what used to be younger sister is now a much older great-grandmother. And so that's the kind of stories that can play out in science fiction movies that you watch. But it's not science fiction in terms of the physics that's being discussed there. That's the way that the universe actually is. That time runs at different rates depending on where you are. And if you want to see that in its extreme, you go to the vicinity of a black hole. But you don't have to go to a black hole to see this, what's called time dilation. Right? Even here on Earth, all the time dilation is occurring. We often nowadays are using our GPS, our global positioning systems, to give us directions from one city to another. And those GPS satellites are up orbiting around the Earth. They are in a weaker portion of the gravitational well of the Earth than we Earthlings are down here at the surface. And so what that means is that clocks on those GPS satellites run faster than clocks down here on the surface. And if you're an engineer who is developing these GPS systems, you've got to take that into account. If you just pretended that time ran at the same rate for the GPS satellite high up there as it does down here on Earth, then you would be making an error that would accumulate over time. and you wouldn't no longer be able to accurately relay information like locations and times of day to people back down on Earth, because the clocks would no longer be synchronized. So built into systems like that is the knowledge that the clocks are running at different rates. If you take two atomic clocks, the best that people can build, and you put them on airplanes, well, leave one on the ground, and its synchronized partner you'll put on an airplane, and fly it around, and then bring it back and put it next to the other clock. The clocks will no longer be synchronized. So because these effects are small near the surface of the Earth, we grow up being unaware of them. Our intuition teaches us that time just marches along at a uniform rate for everybody, no matter where they are. But that's not actually the way the universe is. Here's an interesting plot. There are actually two different ways to dilate time. The one we've been talking about is due to general relativity, gravity, and it's that as you go to higher and higher elevations above some gravitational source, time will run faster and faster. Or more the other way around, as you go in closer and closer to it and its event horizon, time runs slower and slower. Now there is another way to dilate time, to stretch it out, and that's just simply to move along at a speed. So in the example where I had an airplane flying around, there was actually two effects that were playing out at the same time. Time would be dilated because of the motion of the airplane as well as because of its elevation. And if you have astronauts orbiting around the Earth, then you do have both of these effects going on, or the GPS satellites have both of these effects going on. The moving clocks will run slowly, and as you go to higher elevations, clocks run more quickly. So those are actually two competing effects. And it's an interesting question to ask, and this graph here will answer it for us, as to which of those effects win out. And so what we have here on the horizontal axis is the distance from the Earth's center. This vertical line represents the surface of the Earth. And then the vertical axis represents the time dilation that you have in picoseconds. A picosecond is 10 to the minus 12 seconds. And so if you're right at the surface of the Earth, you can see that imagine you were orbiting right at the surface of the Earth. Well, clocks would run on your orbiting spacecraft slowly because the spacecraft is moving. You're at the same gravitational field as everybody else on Earth, and so there's no effect there, and so your clock would run more slowly. As you orbit higher and higher and higher, here's the break-even point, where the slowing down of your clock due to your speed would be offset by the speeding up of your clock due to gravity. And so at a certain elevation, a bit shy of 10,000 kilometers above the Earth, those two effects would balance one another. Any higher than that, then the gravitational dilation wins out and your clock actually runs faster because of that higher elevation. Now, you may wonder, are black holes real? Is this just somebody's idea that exists? Or do we have evidence that these things are really out there in real life, in real space? And it's the latter. As best we can tell, these guys exist in plenty. All right, we've seen them in more than one way now, as we'll discuss. When you're looking for black holes, there's really one good way, if you're looking in light, to view these things. You look for a companion that's orbiting around it, and that's what this image here is representing. This is actually the center of our galaxy. Right there, there's a black hole that's 4 million times the mass of the sun. And we can say that with confidence, as we'll be discussing in more detail in the next chapter, because we watch stars orbit around it. And we can, by the size of their orbits and the time that it takes them to orbit, determine what the mass of the object they're orbiting around is. So by using the orbital properties of a companion or companions, we can tell what the mass of the object is, And if it's small enough that it can't be anything other than a black hole, it's a black hole. The other way to do it is also to look at orbiting objects, but here it's a continuous gas. This is M87, the same galaxy we talked about in today's astronomy picture of the day. Here's that jet that was shooting out from that galaxy, and here we zoom in even closer with the help of the Hubble Space Telescope, and there's gas that's orbiting around this black hole. And from how quickly that gas is orbiting, you can measure the mass of the black hole. We'll talk about examples of each of these cases on following slides. But the idea is the idea is that it's a black hole and not a star if its mass exceeds that of the maximum mass of a neutron star. If it's more than 3 solar masses, then and it's in a size that is very compact, then it can't be anything other than a black hole. So here we have a famous stellar mass black hole, Cygnus X-1. At the end of this semester, we're going to teach you the constellations to look for during the summertime, and Cygnus is going to be one of them, Cygnus the Swan. This is Deneb in the tail of the swan and Alberio in the head of the swan, and roughly halfway between Deneb and Alberio is Cygnus X-1. It's not something you can see with the naked eye. The X here stands for X-ray. You need an X-ray telescope to see it. And what you're seeing is, of course, not the black hole directly itself, because light cannot escape from a black hole. But what you see is the accretion disk around a black hole. We talked about accretion disks with white dwarfs and with neutron stars. Here we have accretion disks around a black hole instead. It's in a binary. Matter from a companion is falling down onto the black hole into the accretion disk around it. And that matter can get very hot and therefore emits short wavelength light in the X-ray that we can view with telescopes like the Chandra X-ray telescope. So by modeling this system, we can tell that the black hole with this accretion disk is about 20 times the mass of our sun. M87, I mentioned it 2 slides ago. It was the astronomy picture of the day. Here's that zoomed in Hubble Space Telescope image of that galaxy's central region. And here they've drawn a little red circle for us, here a little blue circle. That's because the light has been red and blue shifted respectively on those 2 sides of the center of the galaxy. That's what these spectra over on the left are showing us, right? On this side, the gas here where it's blue is moving toward us a little more than the galaxy as a whole. And so that compresses the light from the Doppler effect. It blue shifts it. It shifts it down to shorter wavelengths. And then on the other side, the light, because the gas is orbiting around like this, into and out of the plane of the screen. And here it's moving, let's see, toward us. That's the blue shifted side. And then it goes around and it comes out and it's moving away from us on the other side. So it goes around, and I should say goes in, away from us on the other side. And so there, the light from that gas is red-shifted. It's stretched out. So by looking at the spectral lines of this orbiting gas and seeing how it splits, you can figure out how quickly the gas is orbiting. And if you then also know how far this is by other means, then you can determine how massive an object is being orbited around. And the mass in the center of M87 is billions of times the mass of the sun. We'll learn in the following chapters that having supermassive black holes in the centers of galaxies like this is commonplace. The mass of the black hole in the Milky Way is millions of times the mass of the sun. In the M87, it's billions of times the mass of the sun. It can be even larger than that in some extreme cases. Now, some of you may have seen the Interstellar movie. This movie was actually based on actual laws of physics. And the image that was used to popularize it shows a black hole. this is what you have in the movies. And as of April of last year, as you saw in today's astronomy picture of the day, this is our first image of an actual black hole. And while there are some definite differences between the two of these, there are some similarities as well. And as technology advances, these images of black holes are going to look more and more like what you see in the movie. This is what you would expect. The Event Horizon Telescope collaboration that took this was actually many telescopes from across the Earth that were all trained in on the core of M87. This is just tens of micro arc seconds across in size. This is the tiniest little patch of the sky. It's really amazing. Remember, an arc second is a 60th of an arc minute, which is a 60th of a degree, and there are 360 degrees in a full circle. And so an arc second is already a tiny little angle. And we're talking about tens of micro arc seconds, right? So a micro arc second is 10 to the minus 6 arc seconds. And so this is a tiny little patch on the sky. But by using telescopes and a technique known as interferometry, where the telescopes are spread out over large distances, the whole Earth itself, you can, through the sharing of information among those telescopes, make these very high resolution images. And so what you're seeing here, of course, is not light from the black hole itself, because light from inside the event horizon simply cannot escape. But there's this disk of material that's orbiting around the black hole, and it's light from that disk that we're seeing here. I think the way I'd like to finish today is to give first the answer to today's reading quiz. It is black holes are cool. Black holes are cool is the answer to today's reading quiz. And I hope you'll stick around and watch in the next 7 or so minutes the end of a neat YouTube video that explains why it is that the movies drew the black hole this way, and why I claimed that as we get higher and higher resolution images, we may see things that look more and more like this. So let me go ahead and bring up that YouTube video now.
In this accretion disk, there is dust and gas swirling around here very chaotically. It's incredibly hot. We're talking millions of degrees, and it's going really fast, a significant fraction of the speed of light. And it's this matter that the black hole feeds off and gets bigger and bigger over time. But you'll notice that the accretion disk does not extend all the way into the event horizon. Why is that? Well, that's because there is an innermost stable circular orbit. And for matter around a non-spinning black hole, that orbit is at 3 Schwarzschild radii. Now, in all likelihood, the black hole at the center of our galaxy will be spinning, but for simplicity, I'm just considering the non-spinning case. You can see my video on spinning black holes if you want.
He said the black hole at the center of our galaxy because this was the day before the telescope images of the black hole was released, and it wasn't clear whether they're going to release the one at the center of our galaxy or the one of M87. And they ended up releasing the M87 image, and that's the one I showed you. But the science that he's talking about here is the same for both.
I want to find out more about that. So this is the innermost orbit for matter going around the black hole. If it goes inside this orbit, it very quickly goes into the center of the black hole, and we never hear from it again. But there is something that can orbit closer to the black hole, and that is light. Because light has no mass, it can actually orbit at 1.5 Schwarzschild radii. Now here I'm representing it with a ring, but really this could be in any orientation. So it's a sphere of photon orbits. And if you were standing there, of course you could never go there, but if you could look forward and actually see the back of your head, because the photons could go around and complete that orbit. Now the photon sphere is an unstable orbit, meaning eventually either the photons have to spiral into the singularity or spiral out and head off to infinity. Now the question I want to answer is, what does this black quote-unquote shadow in the image correspond to in this picture of what's actually going on around the black hole? Is it the event horizon? Are we simply looking at this? Or is it the photon sphere or the innermost stable circular orbit? Well, things are complicated. And the reason is this black hole warps space-time around it, which changes the path of light rays. So they don't just go in straight lines like we normally imagine that they do. I mean, they are going in straight lines, but space-time's curved, so yeah, they go in curves. So the best way to think of this is maybe to imagine parallel light rays coming in from the observer and striking this geometry here. Of course, if the parallel light rays cross the event horizon, we'll never see them again, so they're gone. That will definitely be a dark region. But if a light ray comes in just above the event horizon, it too will get bent and end up crossing the event horizon. It ends up in the black hole. Even a light ray coming in the same distance away as the photon sphere will end up getting warped into the black hole and curving across the event horizon. So in order for you to get a parallel ray which does not end up in the black hole, you actually have to go out 2.6 radii away. If a light ray comes in 2.6 Schwarzschild radii away, it will just graze the photon sphere at its closest approach, and then it will go off to infinity. And so the resulting shadow that we get looks like this. It is 2.6 times bigger than the event horizon. You say, what are we really looking at here? What is this shadow? Well, in the center of it is the event horizon. It maps pretty cleanly onto the center of this shadow. But if you think about it, light rays going above or below also end up crossing the event horizon just on the back side. So in fact, what we get is the whole back side of the event horizon mapped onto a ring on this shadow. So looking from our one point in space at the black hole, we actually get to see the entirety of the black hole's event horizon. I mean, maybe it's silly to talk about seeing it because it's completely black. But that really is where the points would map to on this shadow. It gets weirder than that. Because the light can come in and go around the back and, say, get absorbed in the front, you get another image of the entire horizon next to that, and another annular ring, and then another one after that, and another one after that, and you get basically infinite images of the event horizon as you approach the edge of this shadow. So what is the first light that we can see? It is those light rays that come in at just such an angle that they graze the photon sphere and then end up at our telescopes. And they produce a shadow which is 2.6 times the size of the event horizon. So this is roughly what we'd see if we happen to be looking perpendicular to the accretion disk. But more likely, we will be looking at some sort of random angle to the accretion disk. We may be even looking edge on. And in that case, do we see this shadow of the black hole? You might think that we wouldn't. But the truth is, because of the way the black hole warps space-time and bends light rays, we actually see the back of the accretion disk. The way it works is light rays coming off the accretion disk bend over the top and end up coming to our telescopes. So what we end up seeing is something that looks like that. Similarly, light from the bottom of the accretion disk comes underneath, gets bent underneath the black hole, and comes towards us like that. And this is where we get an image that looks something like the interstellar black hole. It gets even crazier than this, because light that comes off the top of the accretion disk here can go around the back of the black hole, graze the photon sphere, and come out the bottom right here, producing a very thin ring underneath the shadow. Similarly, light from underneath the accretion disk in the front can go underneath and around the back and come out over the top, which is why we see this ring of light here. This is what we could see if we were very close to the black hole, something that looks truly spectacular. One other really important effect to consider is that the matter in this accretion disk is going very fast, close to the speed of light. And so if it's coming towards us, it's going to look much brighter than if it's going away. That's called relativistic beaming or Doppler beaming. And so one side of this accretion disk is going to look much brighter than the other, and that's why we're going to see a bright spot in our image. So hopefully this gives you an idea of what we're really looking at when we look at an image of a black hole. If you have any questions about any of this, please leave them in the comments below, and I will likely be making a video for the launch of the first ever image of a black hole, so I'll try to answer them then.
All right, and so then here in the upper right is the image that was released the next day, very similar to what he had expected to see. That's all we have time for today. I hope that you stay safe and take care.